Good. So let's continue our discussion from where we left off last time. We were discussing how to set up the path integral to compute string amplitudes in an honest way. Okay, and if you remember, what we wanted to do was we wanted to compute dx mu dg alpha beta exponential of minus s of x mu g. That's the Polyakov action. Right? This is the thing we wanted to compute. But we wanted to compute this really remembering that diffeomorphisms and Weyl transformations were gauged in this section. Okay? So we put a volume of diff cross Weyl to remind us that that's what we want to do. Right? Because we want to only look at, we want to do the integral over each Weyl and diffeomorphism equivalent class rather than each configuration, because different configurations that differ by Weyl or diffeomorphisms are the same physical configuration. Okay. Now at the end of the last class, we decided on a strategy for doing this. We were going to use the Faddeev-Popov trick. Okay. So the thing that we decided to do was the following. Consider a metric, some standard metric. Okay. Consider some standard metric, and we introduce some parameter tau to keep track of the number of parameters we needed to parameterize standard metrics, or more precisely, the number of parameters we needed to parameterize Weyl and diff equivalence classes. It's going to be some finite number of parameters, continuous parameters. We call that tau. So then g of tau, g0 of tau, there's an alpha beta, minus the actual metric that we have. This is g alpha beta. And then what we did was we took this, it doesn't matter really where, but let's say we put this gauge transformation, which was both Weyl and diffeomorphisms, okay, on this g0. And then we did an integral d tau and d omega. And then we put a delta fp to compensate for the measure. Okay? And the delta fp was defined so that this integral would give us 1. Now firstly, this definition makes no sense if the delta function never clicks along your integration domain. But we have precisely chosen things carefully so that it will always click over the integration domain. Okay? Because we have precisely chosen things so that we have in every there is a G0, per equivalence class. Okay. Taus are labels for equivalence classes. So, if there was a metric and its equivalence class, some standard metric and its equivalence class didn't cover our metric, that's fine because we're integrating over all equivalence classes as well. So one of these integrals will come and hit our metric. Is this clear? Okay. After we go through this, I will come back to deal with one more subtlety. Okay. The subtlety is that what we've done here may not have completely fixed gauge. But I'll come back to deal with that at the next round. Okay. We'll do that today itself. So just so that you don't have to deal with too many things in your mind at the same time. What? Say it again?
This second you mentioned is this combination of Weyl and diffeomorphism.
Exactly. It's basically conformal transformations. Exactly. It's well-defined conformal transformations. So we know that those exist on the sphere, right? SL2R times SL2R. It's well-defined everywhere on the sphere. So we have to, those are not fixed, and that's a non-compact thing. So you can't just live with the volume of that. So we have to fix it. But we come back and do that.
So the second G alpha beta over there, that's some gauge fixed, right?
From the point of view of this identity, it's just any metric. Okay, but we will choose it to be the metric that we're doing the path integral of.
Omega defines diffeomorphism and Weyl.
Yes, omega is both kinds of gauge transformation. Okay. What?
What is the function?
That delta fp. That's the next question. So now what does this delta fp depend on? Now I want to argue that two g's that are related by gauge transformations have the same delta fp. Okay? So this thing is, there's g naught which is put in here. That is integrated, and naively it's a function of g alpha beta, right? It's some function of g alpha beta. But now I want to argue that this function of g alpha beta is a gauge invariant function of g alpha beta. Okay? How do I make that argument? So suppose I start, so this is delta fp of g alpha beta. Okay? Now I want to know what I can say about delta fp of g alpha beta with some auxiliary gauge transformation. Let's call that omega prime. Okay? So by definition, d tau d omega delta of g naught of tau alpha beta omega minus g alpha beta omega prime. This omega is being integrated over omega prime is some fixed number. Times delta fp of g alpha beta omega prime is equal to 1. Now I'm just using the definition for the transformed g. Okay? Now what I will do is something that Indranil suggested at the end of the last class. Namely, I'll do a change of variables. So what I will do is take this quantity and gauge transform the whole argument by omega inverse. Omega prime inverse. Okay? I'm going to assume that this measure is gauge invariant. So it's like an analog of the Haar measure over a finite group. It's a matter for mathematicians and so on to debate about whether these exist. We'll assume it exists. Okay? Okay, for this crazy group. I'm going to assume that this measure, whatever it is gauge invariant. Okay? So then once I do that change of variables, I get no Jacobian for the change of variables because the measure was gauge invariant. Okay? This gauge transformation undoes this guy, but turns this into omega times omega prime inverse. Okay? But because we can change variables to omega times omega prime inverse, measures gauge invariant, that goes back to this formula. So delta fp of g alpha beta omega prime obeys the same equation as delta fp of g alpha beta. This equation completely determines delta fp. Okay? And therefore, we conclude that delta fp of g alpha beta omega prime is equal to delta fp of g alpha beta. Is this clear? Okay? It may sound a bit abstract. It's completely, what we're saying is if you're doing an integral over polar coordinates, you're doing an integral of a radially invariant function. And a simple example of this is the following. See, a simple example of this is take a finite case. So our integration space is Rd, dx1, dx2 up to dxd. And let's say that we are interested in doing an integral over a radially invariant function, a function that depends only on radius. Okay? Now, you know the right way to do that, right? You pick up a measure factor. You just have to do the integral over R, and then you pick up a measure factor, which is a constant, times r to the power d minus 1. So you have r to the power d minus 1 dr. You can get that by following this trick. The analog of rotation, gauge invariant gauge transformations here is rotations there. Okay? This delta fp is the effective measure factor. Okay? And all we're saying is that this measure factor only depends on r. It doesn't depend on, it's basically an obvious thing. The measure factor depends on the gauge orbit. But we've given an algebraic proof. Okay, questions?
Normally, if I have a delta function, right? Delta x minus x prime.
Yes.
And then I would say, rescale my x by 1 over alpha, right? The delta function would pull out a compensating factor, right?
You're saying delta of ax.
You get divided by the derivative.
is equal to 1 over A
Right.
times delta of x. Correct.
And so we heard this thing that we're saying is that we're only allowing such transformation such that that compensating factor is equal to 1?
No, this compensating factor is this thing.
Uh-huh.
You see, we're doing an integral over omegas,
Right.
but the argument is not omega. It's the omega transformation of G.
Okay.
Okay? So the more accurate analogy is this.
Oh,
Then
okay, I see. Yeah. Right, so this is exactly what that is.
that's what that thing
It's
is.
just making sure that this delta function.
It's a way of calculating that measure factor.
function is always 1.
Exactly, exactly, exactly. More accurate analogy would be delta of f of x.
Right, and then divided by
F prime of A. It's like that. Okay? Excellent. So now that we've got this we've got this we see that this thing is gauge invariant. We might as well set this G to be G naught of some tau naught, because in every gauge orbit,
Some omega now, right? Not some tau.
no, we can set G alpha beta, we can choose omega prime
Yeah.
to set it to be equal to this value
Right.
for some value of tau.
Mm.
Because there exists a value of tau such that G is gauge equivalent to G naught at that value of tau.
Yes.
I don't know what that value of tau is, let's call it tau naught. Whatever that value of tau is, there is some tau naught for which it's true. Okay? So, in order to compute this delta Fp, because it's gauge invariant, I choose the representation at G equals that tau naught. Okay? So, my equation for delta Fp becomes d tau d omega delta of G0 of tau omega alpha beta minus G0 tau naught alpha beta times delta Fp. Okay? Times delta Fp is equal to 1. Now it's clear that this delta Fp can only depend on tau. So tau naught in this case. Right? Because it depends on this G0 substandard form. The only information about where we are evaluating it is tau naught, which is very physically sensible, right? What we're doing is converting the integration over all metric space into an integration over equivalence classes. But there's a measure factor associated with what weight to give different equivalence classes. Just like in polar coordinates, there's a measure factor. This sphere contributes less than this sphere. The relative ratio is r to the power d minus 1. That's what this Fp will be. You'll see, as this comment may have been out of turn, but you'll see it. Okay. Now all's good. Okay. Now everything is good, and all we need to do is to now do the calculation. Okay. So what we need to do is to understand how G0 transforms under an infinitesimal Weyl transformation and an infinitesimal Diffie-Hellman. But we know that. What is the change of G? You see, when we've got a delta function, we only care about the infinitesimal deviation from 0. We only care about the argument of the delta function to first order around 0. That's f prime. In order to calculate that f prime, we only need the first order deviation. So we just need to expand. We know that this at identity clicks. So we just need to expand this to first order in infinitesimals around identity. Right? So omega is an identity plus something small. We'll parameterize those something smalls and compute what this is. Okay, so under diffeomorphism, how does a metric change? Well, delta G naught alpha beta, okay, is del alpha, let's call it V beta, plus del beta V alpha. Right, where del is the covariant derivative in the metric G naught. V is the infinitesimal diffeomorphism. And how does G change under an infinitesimal Weil transformation? Okay, clearly plus delta phi and G naught alpha beta. Okay, all good? Okay. And therefore now we just plug this in. Okay, so we plug in. Okay, also we need to know how G transforms on an infinitesimal change of tau, but that's just given by the derivative. So let's say there are some I taus, tau I. Okay, so we get plus del G by del tau I, delta tau I. All good? Okay, we plug that in. So we have d tau I, d v alpha beta, v alpha, d phi, or delta phi is called. Let's remove this delta. Phi is infinite. D phi, this is d, these are path integrals, but this is an ordinary integral. Okay, and we've got this delta now of what? Of this stuff, right? Because the one part just cancels. What remains is this. Okay, so delta of del alpha v beta plus del beta v alpha plus phi g naught alpha beta plus dg by d tau I delta tau I times the Faddeev-Popov determinant. Is equal to 1. Sorry. What? Why can there be many towers? That's the question. It's because it could be that not all metrics are related to each other under Weil diffeomorphisms. Okay? It's like this. Suppose the space of metrics, and I'm drawing equivalence classes under Weil diffeomorphisms. Suppose the equivalence classes are the shell kind of diagram. Then what we have to do is to integrate. You can't bring all these guys. So what we have to do is to choose some slice along these, and these slices are labeled by taus. This cut is our choice of G naught, and then we do the integral. I is the number of parameters that we need for these shells. I abstractly called it tau, but we don't know how many parameters there are on these shells. Is this clear? Okay?
So in 2 dimensions, what is the number of moduli? In 2 dimensions?
The number of moduli for
the number of eyes.
It depends on the genus. I got the formula wrong last time. It was 3g minus 1. 3g minus 1. For g greater than or equal to 2.
Oh.
2, it's 3g minus 1. Okay, but some number, it doesn't matter. Depends on the Okay, I think I said 2 last time. 2g, it's 3g. Okay, fine. So let's go. And that's the number of complex moduli. So that's the number of left moving and the equal number of right moving. We'll see all that. We'll prove all this.
That's the number of moduli.
That's the number of these holomorphic taus and then anti-holomorphic. Why they split into holomorphic, anti-holomorphic? We'll see. Okay. Now let's keep going. You see, delta functions are sort of a pain to deal with, but there's a lovely integral representation of delta functions. Okay, the integral representation is that e to the power I alpha x integral d alpha is equal to delta of x times some 2 pi's, which of course we don't keep track of. Okay, so we're going to use that integral representation here.
This will be a functional integral.
A functional integral. So we will get, basically we need for every, we've got a delta function for each metric component at each point in space. So we need a Lagrange multiplier field which has as many indices as metric. So it's 2 tensor. And at each point in space. Okay? We want to make it diffeomorphism invariant. So what we get is this. E to the power I, let's call it B, square root G naught B alpha beta, okay, times del alpha B beta plus del beta B alpha. Now V, this will be V alpha plus phi G naught alpha beta plus d G naught by d tau alpha beta del tau I times delta Fp is equal to 1.
Delta what?
Delta Faddeev-Popov.
Okay. No, and the functional integral is over
Now the function. Thank you. So now we have all the integrals we had before, but also a dB. So d tau I, dv, d phi, and dB. All good? I've just represented the delta function with
this is d here?
I'm sorry, this is delta tau.
No, I mean, what is this?
That's alpha beta.
Okay. Right.
I'm sorry.
I'm
Okay? Now you see the nice thing is now delta 1 by, so now we can just take this Faddeev-Popov determinant, since it was gauge invariant, it can be pulled out, right? It's not a function of any of these. It's just a number depending on tau naught. It can be pulled out, it's 1 over delta Faddeev-Popov is that quantity. Okay, so we've got a representation of the Faddeev-Popov as 1 over the Faddeev-Popov determinant as a path integral. That's nice. But if you remember last time what we argued was that once we use this delta function and plug into here, we're going to plug this in here, use the delta function to the G integral, and what will be sticking up is the Faddeev-Popov determinant. We've got a nice representation of 1 over the Faddeev-Popov determinant. But what we want to put inside our path integral is not 1 over the Faddeev-Popov determinant, but the Faddeev-Popov determinant itself. So now we use a trick. This Faddeev-Popov determinant is not just, this expression for 1 over delta Fp is not just a path integral, it's a quadratic one. A quadratic path integral is always a determinant. And there's a beautiful trick for inverting determinants in path integrals. You just change every commuting field to an anti-commuting field, and the determinant that would have gone upstairs goes downstairs, or vice versa. Right? And so what we want to do, I'm going to use that, I'll maybe do a little pre-processing before doing that, but the basic strategy is now going to be you see it's quadratic because the variables are b, v, phi and tau, and for every variable inside one can just replace by a fermionic, by an anti-commuting variable, and then you've got an expression for the Faddeev-Popov determinant. Is this clear? Okay, but before doing that, let's, there's some things that are totally trivial, so let's do that and then use that trick. Okay, so just at this level, before doing that, I'll do a few manipulations. You could have done it after, but it's just easier to think with bosonic variables than fermionic things. When I use it, I'll repeat it. I'll just tell you the algebraic identity I'll be using. That if you have e to the power xa, xb, mab, this is equal to 1 over integral dc dca dcb e to the power ca is cb and ab, where these are anti-commuting variables. That way one of them gives you the determinant, the other gives one over the determinant. So if you want to invert a quadratic integral, just replace all bosons with fermions. That's the simple. That's basically. Okay.
And because you are dealing with complex, you don't have to use square root of determinant. Right?
Yeah, you see, whatever this was, I'll do the same here. So these were independent real variables. I'll replace them by independent real fermionic variables. You see, because suppose it was a square root of a determinant, on the other side also I'll get a square root of it. I just have to invert it. I don't think too much about what it is. Okay? But before doing that, let's process this a bit. Now, the thing I want to do is the following. You see, one of these integrals is utterly trivial. And that integral is the integral over phi. Okay? That integral is utterly trivial because it just forces b to be traceless. Okay? So you see that the integral over phi is just going to tell you that b is that instead of doing an integral over all two tensors b, we will only do an integral over traceless two tensors b. Okay? Since we know we're going to get this anyway, we might as well remove the trace part out of this, because it's going to contract with b and b is going to turn out to be traceless. Because you see this is phi times g0 alpha beta contracts with this, and that's the trace of b. So you have an integral of
The Lagrange multiplier.
we have integral of e to the power I phi times something d phi. That is delta of that something. Okay, that something in this case is trace of b. Okay, so motivated by that observation, let's remove and add and subtract the trace part of this. Okay, so we'll write that as del alpha v beta plus del beta v alpha minus 2 times minus half times g alpha beta, no, just as it is, I suppose. G alpha beta, I'll get the 2's right in a minute. Del dot v plus g alpha beta del dot v. Now, if I take the trace, I get 2 del dot v and 2 from here, so that's okay. Okay? So I add and subtract this. Now this g alpha beta part is added to plus phi, which was there anyway. Now I do the path integral over phi. As we just discussed, it sets trace of b to 0. So this part gets multiplied by 0, so it's not there. Okay, so I mean, I'm saying once we know b is traceless, you can either put this or not put it. It will make no difference. Okay, so we've simplified a little bit. Our simplification is now d tau I, d v alpha, d, no d phi, db, but now db is only over traceless tutors. Okay, and exponential of I square root g naught b alpha beta, okay, then this traceless part, del alpha v beta plus del beta v alpha minus g alpha beta del dot v. Okay, and then this part is now gone, this part is still there, plus dg naught by d tau alpha beta d tau. Every g is a g naught, I'm sorry. I'm not writing it, okay? It's okay. G naught. Yeah. Okay, that's great.
This is probably getting ahead of the story, but is this leaving the calgram?
No, no, no. This BAI is just unfortunate notation.
I see.
It's going to turn into the ghost field,
I see.
the bosonic ghost field in just a minute. Okay. Now there is one more thing I want to do, and I have to decide whether to do that before or after continuing to just a minute. Okay. Let's just do it. I just want that. You want me to use it to make it a delta function? That's what you're saying? Yeah, that's exactly what I was wondering, whether it would be better to do that before or after continuing this. Let me do it after. Let me do it after. So now what I'm going to... What? That is delta tau I.
Yeah, but now I'm saying you change the variable and just make it tau.
No, it's the infinitesimal change in tau.
Yeah, I know. So it just changed from tau 0, right? So I can just shift my variable tau.
No, it's a formal infinitesimal. Just like this V here was a formal infinitesimal diffeomorphism. See, our metric was at some tau naught. And then in the integral we went from tau naught to d tau. That's what this delta tau was.
Yes, yes. No, I think he's asking just the way we integrate over the phi field.
Yeah, to do that, you have to delta tau should be tau. I mean, because the integration is not being done over delta tau with tau. So I'm saying there's this shift of
Realization instead of delta phi was phi.
Yeah, this is a formal small change. This tau naught,
yeah.
you see tau naught lived in here and tau lived here. This tau went from tau naught to tau naught plus delta tau,
Yeah.
and that had to be integrated over.
Yeah, so I think what he's asking is the integration variable, we can make a change of integration variable from in that
That's what I'm saying. It's I just
You're saying this and this, are they the same? That's the question? That's the question? Yes, that is that is correct. That is correct. Yeah, so we can call this delta tau if you want. Just a minute. No. Just a minute. Yeah, that's fine. It's just some variables. Let's call it delta. That's good.
Yeah.
That's good.
That's just about the unperturbed.
That's good. Now what we're going to do is to take every bosonic variable. So this is an expression for 1 by delta fp. Now we're going to take every bosonic variable and change it into fermionic variable. Okay? So V alpha will go to a variable we'll call C alpha. Okay? And B alpha beta will go to a variable we call B alpha beta. And delta tau, you choose alpha, zeta. Delta tau I will go to zeta. The important thing is that each one of these is now anti-commuting. Okay? And so we get the expression delta Fp is equal to the same expression but with B replaced by, okay, so delta Fp is equal to this, and now d zeta d C alpha d B alpha beta B C C G naught C G naught zeta. All good?
So that zeta is costal for the tau, but there was no functional integral over tau.
Yes.
And now the costals have their own, and they appear in the path integral measure as well, right? So how do I
What does that mean? Now let's just do it. You see, now with the zetas like this, we can just do the integral over zeta.
That derivative is also equal to
What?
that derivative is also dg naught by d tau.
No, that's d g naught by d tau. That's just a function.
that was the original
G naught was a bosonic function of tau, right? Okay, so this and there's a corresponding zeta. Okay, now see, when we're looking at fermionic variables, anti-commuting variables, there's this lovely identity which is exponential of AB integral dA is equal to B. Okay, how do you prove this? Well, what is e to the power AB? By definition, e to the power AB is the Taylor series expansion of e to the power AB. But these are anti-commuting variables, so it's 1 plus AB. Integral of 1 is 0. That's how fermionic integrals work. And integral of AB over A is B. It's up to a sign which we're not being very careful about at this stage. Okay? In fact, it's a general fact that the linear function in a fermionic variable is the analog of the bosonic delta function. Because suppose you have a function like A plus B times A, where A is the fermionic variable. Okay? If you want to pick out the value of this function at 0, that's A. So the delta function should be that quantity which when multiplied by this and integrated over A gives you capital A. Okay? But if you multiply this by A and integrate dA, this is 0 because A squared is 0. So, and this integral A dA is 1, so you get capital. So X, fermionic X, has all the same properties as bosonic delta function. And indeed, from that point of view, you could have guessed. Because for a bosonic variable integral, for an I to be fancy, bosonic variable e to the power I AB integration over A is delta function over B. The analog of a delta function for a fermionic variable is just the linear function. Is this all okay? Okay, great. So now we're going to use that here. Suppose there weren't many indices I. Then the integral over zeta I would have just given us dg naught by d tau times b. Okay? If we've got many variables because of the anti-commuting nature, you can convince yourself that what you'll get is the determinant of the matrix. Okay? So now let's just do the integral over zeta I. And actually forget it. Let's not be so fancy. In fact, it's even wrong what I said. Sorry. It's just product over I. Let's just do that. So what we get is product over I. Is it right? Just d g naught by d tau I b alpha beta. Yeah, just one, nothing much, just one for each of the zetas. Just use that formula repeatedly. It's not, it's a vector structure, not a matrix structure. What I was saying would have been for two of these. Yeah. What? Yes, you're absolutely right. Root G0 and I's will, we're not being that careful. But root G0 is a good point. Let's put that. Okay? So for each of these measure factors, for each of these zetas, what we get is this additional factor. And what's left is the really important part, the thing that's upstairs. What's left is the really important part, the thing that's upstairs, which is exponential of square root G B alpha beta P. Okay. Let's write it out. V beta plus del beta V alpha minus del dot V G naught alpha beta. Where these quantities here are fermionic variables. Sorry, thank you. C, and then the integral over dB dC. Okay. Now, before proceeding to massage this further, let's just actually use it for what we wanted. So you remember what we had was path integral over the metric of the Polyakov action. Then we insert the identity that integral, let me do that in equations. What we wanted to compute was integral dg dx vol gamma times exponential of minus s Polyakov x and g. This is what we wanted to compute. Then we had this beautiful identity which was integral over d omega d tau delta of g naught of tau omega minus g is equal to times delta fp of g, which will be basically of tau, will be equal to 1, is 1. And now we have this lovely expression for, so let's first plug this in. We put this 1 inside here and interchange orders of integrals. Then we use this delta function to do the integral over g. So we get that what we want becomes integral dx by volume of gamma times exponential of minus sp of x and now g naught of tau, because of this delta function. Okay. Then there was this integral d omega d tau. The delta I've used up, but the delta fp, so that's e to the power minus s times this business. So to this all we add is plus s ghost, where s ghost is this quantity. And now the integral goes over dx, db and dc.
And not over d omega and d tau.
At the moment it's still there, but the whole thing does not depend on omega. So this part kills this, but this is still there.
Yes, yes.
Which product term? And that's there. Times this business. So this is the path integral that we wanted to compute has turned into this path integral that we will go ahead and compute. What?
That ghost action is up here on the right?
That ghost action is up there. Yes, S ghost is equal to integral square root g b alpha beta del alpha c beta plus del beta c alpha minus del dot c g alpha beta. Okay. For bosonic integrals, whether you put an I here or not matters. For fermions, it makes no difference at all. Just absorb it into B goes to I times B. And the question of whether it converges or not is not an issue. It's fermionic. Okay, so you can put it or not it's up to you at will. Okay. Now this looks pretty nice. This looks pretty nice. And in order to understand what is going on here, let us first specialize to a special case. What? Yeah, not equal number of C's. Actually, you'll want, you see that there's going to be some zero modes in this action. We'll see that in a bit. We don't need equal number. We need some number of C's.
So some number of C's so that the non-trivial part of this B gets 2 point something.
Well, you see there are going to be zero modes in the BC sector, and that will absorb some of these insertions. Hang on, we'll discuss this. So we don't need equal. So you'll need some number of C's, I agree. Okay. It's coming, all coming. Hang on for 2 minutes. Okay, maybe we should immediately deal with the invariance question. Okay, now Indranil's question really has to do with the fact that we have pretended that we've done something inaccurate. We've pretended that what we've done fixed gauge. But it's possible, and indeed the case, as we see for the case of the sphere, that fixing to a particular metric up to violent diffeomorphism does not completely fix gauge. These are precisely conformal transformations. Conformal transformations are precisely those Weyl transformations and diffeomorphisms that do not change the metric. Now when we will be integrating over some nice Riemann sphere, so most of the conformal transformations we dealt with in class are ill-defined, either at 0 or at infinity. But as we have seen in our discussion, there is a particular set, namely SL2R times SL2R, that is well defined over the whole sphere. So we have done something a bit wrong, because although we have tried to fix gauge, we have not completely managed to fix gauge. And the thing that we have not completely managed to fix is infinite volume. So if we try to do this path integral, the answer will be infinity. Because we will do the integral over an infinite, the infinite number of configurations, all of which give the same answer. So infinite volume. We've not see, this modding out by all omega was inaccurate. We've modded out by everything that we fixed. But we've not fixed some part. On the sphere, the part that we've not fixed is SL2R times SL2R. Okay, that part we have to deal with. So we have to understand how to complete our gauge fixing. Okay? Now, in order to do that, we have to go back to see what we are really interested in computing. In the last lecture, I told you what we would be really interested in computing. I told you that what we would be really interested in computing is to put vertex operators here. These are the scattering amplitudes, the states that come in. Okay? To put vertex operators there and integrate them over the whole world sheet of the metric. Okay? Now, whatever we do, we cannot break our Weyl plus diffeomorphism invariance. That is like a sacred principle for us. Because what we really wanted to do was to work with that Nambu-Goto action. Number auto action had diffeomorphism invariance, fine, and it just didn't have that while factor. Okay, so we want to keep that fact. Otherwise, we're doing something different from working with the number. So whatever insertion we put in should also be while and diffeomorphism invariant. Okay. So now let's see. Suppose something's diffeomorphism invariant. It must take the form square root g times v, where v is a scalar. That's the only way an insertion of an operator can be diffeomorphism invariant. Of one operator can be diffeomorphism invariant. Got indices, nothing to contract with. Okay? What about if it's while invariant? Now that's more interesting because this factor of square root g is not while invariant. Okay?
Some scaling.
C is v and v is -1.
Oh, well, that's going to come, but we're going to get it from logic. See.
No, I'm saying that you renamed v to c, right? V has dimension, v was coming from x going to x plus v.
Correct.
Therefore, v has a dimension of a length.
Correct.
It is 1 by mass.
Yeah, but you know, there's some issues there because v is a vector field, c is a vector field. So to just put something here, though we're going to do something very similar, but hang on. Okay, so, but there's something just more elementary, which is what is the transformation of g under a while rescaling? Well, let us work with the convention that g goes to g times e to the power minus 5. With this convention with the minus here, with g alpha beta. With this convention, we're going to match with our usual notion of dimension, as I will show you in a minute. So if we work with this convention, so little g alpha beta has weight -1. Square root of determinant of g also has weight -1. Because the product of two of these and then a square root under while transformation. So v here had better be a scalar operator that transforms under while transformations with weight +1. So now, suppose v was an operator that under diffeomorphisms was a scalar, but under while transformations transformed with weight +1. Under conformal transformations, how will it transform? Under conformal transformations, how will it transform? And
Just the while transformation.
well, just a while, and that you see something that transformed like a tensor plus while weight is what a primary operator was. And in fact, this 1 tells you that it's going to be a 1, 1 primary operator. H equals 1, h bar equals 1. Okay? Okay. Okay. Maybe the more standard convention is 2, so I'll put that here. I'll say it again. Suppose G transforms under while rescalings, like G goes to G times e to the power minus 25. Then the square root of the metric also transforms in the same way. So under while rescalings, V will have to transform under while rescalings like V times e to the power 25. Okay? Now, I want to know, so what we've got is some scalar, okay, which under while transformations transforms like V goes to V times e to the power 25. Now from this we can figure out how this V transforms under an arbitrary conformal transformation. Because an arbitrary conformal transformation is a scaling, is a diffeomorphism, times a while transformation that undoes the metric factor. That while transformation that undoes that metric factor was precisely del f by del z, right? Do you remember? Let me remind you. Suppose we have z is equal to f of z prime. Then what is the metric? dz bar goes to, or is equal to df by dz df by dz bar, df bar by dz bar, let's call this w, okay. Okay, fine. W bar, dw bar. So how has the metric changed? It's changed by this factor. Yeah, which is, this is 1 and this is 1. Now you just have to check whether it's 1 or minus 1. That is the thing that requires calculation. But you remember primary field was defined as something that under analytic part transformed like df by dz to the power h. So you can clearly see that we're getting that this V has to be either primary field of weight 1 or a primary field of weight minus 1. I'll leave that exercise to you. Check it's actually weight 1. These minus signs are always hard to get. You work it out at the scaling, you'll see. Okay? So what we have to do is to put here a primary operator of weight 1. What we wanted to scatter was something in the x sector, right? We wanted to scatter something in the number go to action. So what we're supposed to do is to put some operator here, which is a while operator of weight 1, which we know now because we understand the x sector so well, is some primary operator of weight 1, 1 comma 1, inside here. So the basic formula that I started writing down missed these factors. I didn't want to compute a partition function, I wanted to compute an S matrix. So in addition to this, what I wanted to do was product J is equal to 1 to m integral G times V d sigma, one such factor for each scattering amplitude, where V was some primary operator built out of the matter sector, built out of the x's of weight 1 comma 1. How this primary operator matches, for it all to make sense, it had better be that what I'm saying matches to the spectrum of the theory. Because what we actually want to do was scatter states. So this mathematical construction there had better be a one-to-one map between what I'm saying now and the spectrum of the theory. I'll show you that. Yeah, please go.
Do we have an argument that H always has to be positive?
Yes?
And then over here we have something with positive H and negative H.
Well, this G is not really an operator in our theory. It's just a formal object. The G is some quantity. Okay? But this thing is going to be a genuine operator. Is this clear? Okay? This is the thing we really wanted to compute. This is the part that I suppressed so that we wouldn't have to do everything at one shot. Okay? Now, but we have to remember that we have this. So suppose the number of diffeomorphisms we have not fixed, okay, is, I wanted to call it C, but that's a ghost field, is gamma. Then I don't know, we need to give a name. E. I don't know. F. The number of diffeomorphisms we have not fixed is F. Okay? So we have F unfixed diffuse. Those are these, exactly. Those are these. Okay? And we'll analyze for every genus what we get for each of these ambiguous.
Why do we think that it's like, maybe I'm just misunderstanding, it's
Please.
a discrete number, not that it's a continuous parameter?
It is a continuous parameter.
Okay, what is calling that?
But the number of continuous parameters. Okay, so sorry, it's just like the number of moduli here. This tau was an integral, but how many variables do I need to integrate over the manifold of taus?
Right, so, but tau is sort of, let's say, some real number or some real manifold, but over here, the freedom and diffeos is like the space of functions.
I mean, it's just
But
one,
see,
function.
let's take a look at this on the sphere. On the sphere, it was the set of conformal transformations, which sounds like an infinite number of things. However, they have to be well defined.
So that would be a soul.
That's SL2R times SL2R. So it's got 6 parameters.
Is that generic?
Yes, it's always true. In fact, on the sphere, it will be 6 parameters. On the torus, it will be 2, and a whole higher genus surface is 0. Okay. Yeah, so all this we understand very well. So this derivation is being given with a lot of hindsight. It's not how it would have first been worked out. Okay. So, great. So now we have these many f unfixed diffeors. On different genus G surfaces will be different numbers. Okay, we've got these f unfixed diffeors. How are we going to fix these diffeors? We have this beautiful way of fixing diffeomorphism invariance by moving to conformal gauge. Not messing around with the x's, because that would break Lorentz invariance. Not doing the analog of a light cone gauge. We still don't want to mess around with the x's. We've fixed a metric to the extent that we can. So what's left? Well, let's fix some of these points. Okay? By these are just scalars. By using diffeomorphisms, I can take my scalar and move it to some fixed locations. Okay? So if there are f or really 2f diffeomorphisms, 2f in the real number sense. Right. So if there are 2f in real number sense diffeomorphisms, 2f parameters in there, that will be enough to fix the position of f of the locations of f of these quantities.
You mean the vertex operators?
The vertex operators. So these guys were integrated. These had a v of sigma I, d sigma I. So the thing that I really should have done in my Faddeev-Popov trick, sorry, everyone's looking confused. Please stop me. Everything here is very simple except the board's too small to be systematic in notation. So it's all very simple. So stop me, whatever's confusing.
So many degrees of freedom to basically saying every scattering you want to compute with, let's say 4 legs, there's essentially one formula for it. My gate freedom allows me to sort of fix the same here.
Well, I won't be able to fix all of them.
Right, up to some fixed number, right? Up to some fixed number of scattering.
Yeah, up to
2f.
actually that fixed number will be 3.
Right.
4 you'll still have to do an integral.
It just seems like a very...
Okay, that kind of question I don't know what to say. M is what? No, totally different. M is the number of inequivalent metrics. The number of parameters in the metrics that cannot be related to each other by violent diffeomorphism transformations. Okay? F, on the other hand, is the number of diffeomorphisms that leave a particular choice of metric in an equivalence class unchanged. You see, these are totally different things.
We should have at least that many v's inserted.
Exactly. We should have at least those many v's inserted, otherwise this formula makes no sense. Okay? We will come to physically interpreted all these. The number, this 2f, f is never going to be larger than 3. On the sphere it's 3. Okay? And 3 will play a special role. The reason that this makes sense is this. If you were doing 2, you would be computing a propagator. But string theory forces you to be on shell. How do I know? Firstly, by computing scattering amplitudes, but the thing that is going to make this on shell is the fact that this v had to be a 1, 1 vertex operator. Let's see intuitively why this puts it on shell. See, the simplest 1, 1 vertex operator is e to the power I k dot x. Now, for this to be 1, you remember we found the formula for the scaling dimension of this operator? It's alpha prime k squared by 4. Okay. So the simplest 1, 1 vertex operator is this with alpha prime k squared by 4 is equal to 1. So k squared is equal to alpha prime 4 by alpha prime. This is m in our on-shell condition. M squared is equal to minus 4 by alpha prime. You see, this is the Marshall condition. K is at the momentum. You can't put any momentum you want. You have to be on shell. This, in fact, is the same Marshall condition we got for the tachyon operator in the earlier part of the course. So this is going to be the vertex operator for the tachyon operator. And you see, we cannot take this tachyon operator and put it on a K that is not equating the equation of motion. This is where it's going to come. This is one place it's going to come. there is no gauge invariant. There is no gauge invariant. There's no well-defined formula for an off-shell correlator. Yeah. Not very surprising. In a theory which has diffeomorphisms, off-shell correlation functions are not diffeomorphism invariant. But S matrices are. We're doing a theory of gravity.
Off-shell quantities are not gauge invariant even in electrodynamics. If you are off-shell, then your propagator will
well, for an electron field. However, in electromagnetism there are operators whose off-shell correlators are gauge invariant, namely F square, for instance.
Yes.
There is no analog of that here, because everything is acted on by diffeomorphisms. Diffeomorphisms move the positions of insertions. If you fix a position, you're breaking that diffeomorphism.
There is no way you are going to compute this thing.
You will have to compute something very sophisticated. Now, people talk about off-shell correlation functions defined as follows. You start at infinity. You shoot in a geodesic of a certain length along a certain angle. Insert an operator at the end of that. That is formally a gauge invariant thing, but good luck trying to compute such a thing. This is the analog of your Wilson lines continuity. So I don't want to make a very strong claim that there are exactly no off-shell.
All you are doing, you are putting some operator somewhere and joining it to analog of Wilson line.
To infinity. I'm using the fact that infinity is rigid. Then anything that you define using infinity, let's say an angle from infinity, and some proper length, is well defined. I can formally insert that into at least a semi-classical gravity path integral. This is something that is very popular in discussions in ADS CFT nowadays, as you know. This is how people build bulk operators. Okay? As I say, good luck doing that. Okay, fine. Maybe, firstly, string theory has much more gauge invariance than Einstein gravity. So that thing is Einstein gravity gauge invariant. It's not totally clear it's string theory gauge invariant. Certainly nobody's ever figured out an efficient way of computing such a thing in an exact string amplitude. It's not totally clear it's a completely well-defined thing beyond semi-classical gravity. Okay? Anyway, it's clear that something off-shell will have to be much more complicated than something on-shell. Right? So it's not totally surprising that if you start doing something simple, you get simple answers for on-shell quantities. And maybe, somebody will find a nice formula for some complicated off-shell thing at some point, but it won't be as simple as this. So it's not surprising. Okay? Great. So, but now let's, now since Indranil has forced us, we have to refocus our derivation. Because you see, we did this thing about this at some point in our formula. In some point in our derivation, we have this formula. D tau, d omega, delta of g naught omega minus g delta fp is equal to 1. And I told you we had to introduce this integral over taus, because otherwise you might get 0 here, and so delta fp might have turned out to be infinity. But there was the opposite danger that we didn't worry about. Namely, that this integral is infinity, so delta fp is 0. And indeed, that's what would happen if we don't completely fix gauge. Because the part of the gauge fixing that is not fixed, you have to integrate over that. That's got an infinite volume, so that's what would happen. So what we've done so far is inaccurate. How do we make it accurate? We complete the gauge fixing. Okay? So what do? We put I is equal to 1 to f. Delta of sigma I minus sigma I naught, some specified values, specified locations for the first I operators. And let those be gauge transformed by diffeomorphisms and Weil transformations. Okay? If we put I is equal to 1 to f, then these additional fixing conditions fix the remaining gauge invariance. Is this clear? Is what we're doing clear? sigma I is going to be this thing that this will be integrated over. Sigma I naught is just your favorite location. On the plane, it could be the point 0, 1, and infinity. Okay? You're free to choose them as you like. And then you're supposed to do the integral over this, and then now you've got a well-defined formula. Because this delta fp will now turn out to be neither 0 nor infinity. I have an integral over some sigma. No. The integral over sigma is here. But here I just take the point sigma I take a given sigma. Let's say this could be the point 1, 0. Then there is another point sigma, whatever it is. And I make this guy here. I move it so I do the diffeomorphism. So it takes that point there.
Oh, the omega involves that.
The omega involves that integral, yes. Now the Faddeev-Popov thing is defined by this whole formula. This is the correct formula for the Faddeev-Popov. Before this, the Faddeev-Popov was either 0 or infinity. I could have done it. If I didn't have the taus, I would get infinity. If I didn't have this, I would get 0. I need both of these to get a well-defined formula for Faddeev-Popov. Okay? So now how does this this change things? Well, you see, the first question is, how does, as before, this Faddeev-Popov is going to be gauge invariant. So we might as well choose sigma i's to be equal to sigma I 0. Just like we chose G to be G0. Okay? Then how does omega act on a sigma? Well, sigma is a location of point. While transformation does nothing to it. While transformation doesn't act on coordinates, right? Just acts with the metric. But a diffeomorphism moves it by the amount V alpha. Okay? V alpha has turned into C alpha. Okay? So we had delta of, so what we have is, okay, so let's be systematic here. This delta function will turn into a delta of V alpha at sigma I naught. Is this clear? Just like every other delta function, this one will also be exponentiated. Okay, so we write this as e to the power theta alpha V alpha at sigma naught.
How did you just move the delta function from sigma I minus sigma I naught to the V alpha?
To the V alpha, because this Faddeev-Popov determinant is gauge invariant. So we choose this omega so that sigma I naught sits at sigma I. Okay, or sigma I is sigma I naught. Okay, then the infinitesimal diffeomorphism acting on sigma I naught is V alpha at sigma I naught, because that's the change in the coordinate. Okay, so this thing is delta of V alpha at sigma I naught. Clear? Then I put here, I take this delta function and exponentiate, and then I use my rule. I change every bosonic integral to a fermionic integral. So this becomes C alpha, and this becomes some, okay, this is the same thing, but it's fermionic. Okay? And then I do the integral over theta alpha. So what I get is an insertion of C, an insertion of C alpha on the Riemann surface at the point sigma naught. Okay? But this delta function allows us to do the integral over the first F vertex factor. Okay? And so now our final formula is the following, and I'm going to write it down and you tell me if you believe it. Uh, product I is equal to 1 to m d tau I. Product j is equal to 1 to f c, and then product alpha is equal to 1 to 2. C alpha, because there was over x and over y. Okay. C alpha, now square root g, C alpha at sigma I naught, square root g at sigma I naught, j naught. V, sorry, Vj at sigma I naught then product f j is equal to f plus 1 to the number of insertions to m integral d square root g d sigma I d sigma j Vj of sigma j.
The number of tau is m.
Ooh, m was, am I getting mixed up with, where was my, yeah. Now I wanted the total number, what did I call the number of these? Let's call these m, let's call these n. Okay, now the number of tau i's, as you say, is m, so we have product d tau I, and let's, with this d tau I, let's just put our factors. D tau I del g by del del g by del, what did we have? The factor we had was square root g del g by del tau I b alpha beta b alpha beta times e to the power minus s Polyakov plus s cos. Okay, and then the whole thing is also path integrated over dx db. Let me see. Let me put a box around the final formula, and you see if you alpha is equal to 1 to 2. Different. We need some sort of an identity, and I'm going to show you that. Okay? Hang on. Is this formula clear? Anyone has any issues with this formula? This is one of the central results of bosonic string theory. A formula for determining string scattering. We have to study it in many ways. We will.
If we wouldn't have, if I wasn't interested in calculating just the partition part, and without interested in the partition part, how would I have fixed?
You wouldn't have been able to. Well, you would have been able to at genus 1 and higher, basically. Okay? But genus 0, you wouldn't have been able to. And there's going to be a physical interpretation for that. See, for instance, let me say for the easiest case, suppose you had a scattering amplitude of 2 particles. In genus 1, f is going to be 3. Genus 0, f is going to be 3. On the sphere, f is going to be 3. It's SL2 R temperature. Okay. So suppose you just wanted to put 2 insertions. Because these 2 insertions are on shell, what you're doing is trying to compute 2-point function, like a kind of scattering amplitude, or like a propagator, but on shell. Now what do you know about a propagator on shell? It's infinity, right? Okay? Now, if you have just 2, you haven't managed to gauge fix all of your gauge freedom. There's one bit of gauge freedom left unfixed. So doing the integral will give you infinity. That's the interpretation. The reason you're getting that infinity is you're computing something you shouldn't be trying to compute. Okay? Yeah, so yes, higher genus partition functions contain gauge invariant information. Correct. You see, for instance, genus 1, the partition function tells you about, it's not totally obvious because the partition function on us, but the partition function will, suppose we take genus 1 and we compute this partition function on a thermal circle in space-time. This will give us a thermal free energy of the string theory. Okay. So, yeah.
You have to tell me something about how many instructions are allowed on Torus?
Well, on Torus, you are allowed to put 0. Actually, the answer is you should put at least 1. But the unfixed gauge invariance has finite volume of the torus. It's just rotations of the circles. Okay? So it doesn't matter. You can leave it unfixed. You get a number.
In sphere, it became
Because SL2 are at infinite volume. Okay? It's a general rule that if you leave only finite volume of gauge invariance unfixed, you're free to go ahead and do the calculation. Just divide by that volume in the end. Who cares? The danger is when it's infinity. When it's infinity, you don't have the way of getting a number. Then you have to gauge fix. Okay? Fine. Now there are many things about this formula we need to understand. Okay? So let's start slowly trying to unpackage this formula in all its various bits and pieces. Okay. The first thing about this formula is just to satisfy Indrajit about, the first question you might ask is, look, there are all these C's and B's, and it's very dangerous to have insertions inside a fermionic path integral, because if you don't do things right, you might just get 0. Okay? So the first thing we're going to understand is, first thing we're going to try to understand is why there were these many B insertions and why there were these many C insertions. So now let us examine the ghost action. Else ghost was equal to B alpha beta del alpha C beta plus del beta C alpha minus del dot C G alpha beta square root G. What? Thank you. This was a ghost action. Now, just to be able to talk about this, I'm going to invent the following notation.
number of gluons is same as number of unfixed conformal solutions.
Exactly.
Because this is the same kind of problem.
Exactly. That's the key point. Let me, for this operation, let me invent some notation. I'm going to call this BPC. Now let me explain what I mean. You see, C is a vector field. P is an operator that takes a vector field to a traceless 2 tensor. The operation is this. Okay, so this is how P acts on a vector field. And this inner product, this bracket here is an inner product. Given a field of any index quantity, let's say 2 tensor, I'm interested in defining an inner product on the space of 2 tensors. I define the obvious thing. I integrate by square root G. So suppose I want to define A alpha beta, B alpha beta. I'll define that as integral square root G, A alpha beta, B alpha beta. This is a nice inner product because it's diffeomorphism in there. Okay? So with these definitions, P, you understand, it's this operator. It's a natural operator that takes a vector field to a symmetric to tensor. And then this object here is just giving you the inner product between B and C. Is this clear? Now, I'm going to study this P operator for a little while.
The P operator is symmetric in principle.
Yes.
So then, why did you not? So then it should be the same amount of degrees of freedom, right?
You're just counting?
Yeah.
But it is same number of degrees of freedom, more or less. But sorry, please tell me what point you were making. But these are number B and C insertions in the path integral. It's a different question whether there's the same number of degrees of freedom. But we're going to come immediately to talk about it. So now see, what was this P operator? P operator was precisely, P acting on a vector field V is precisely the change in the metric induced by V, the infinitesimal diffeomorphism C, after you subtract a wild part, a suitable wild part, to remove the change in the trace. That's what it was. Okay? So now suppose I give you a vector field. It changes the metric a little bit. It changes both the trace part and the non-trace part. Then I do a Weil transformation to remove the change in the trace part. That's the best I can do to undo the action of the diffeomorphism by a Weil transformation. So all that the Weil transformation affects is the trace part. Okay? So this is the, so I do a diffeomorphism and a corresponding Weil transformation. Now, suppose after I do these, the change in the metric is 0. Then this quantity for that vector field represents an unfixed diffeomorphism. By definition, basically a conformal transformation. Right? So I'm just saying something that's obvious, but I'm saying it in language that may be new, which is that the zero modes of the operator P are in one-to-one correspondence with unfixed diffeomorphisms. Okay? Fine. Now, the next thing I'm going to do is the following. Since I've got a nice inner product, I can define a dagger. So this can equally be written as P dagger B times C. Yeah, exactly. I just integrate by parts. Okay, so I just transfer every derivative here. This was traceless, so this is not really there. It's just del B acting on C. On traceless 2 tensors, it's just contraction. Okay? So this object here, now as Indrail said, this is an inner product in a different space, in the space of vectors, but that doesn't matter, an inner product. Okay? So this quantity, just by an integration by parts, can equally be well written like this. Okay? We're going to do this a little better by dealing with the operator PP dagger in a moment. But anyway, let's look at it this way. Now let's look at the object P dagger. Okay. Suppose you have 0 modes of P dagger. What does it mean? If you have a 0 mode of P dagger, this means that no matter what C you put in here, okay, so this is just equal to this. Now here, what it means that you had a 0 mode of, if you had a 0 mode of C, then if you put that particular diffeomorphism in here, you will get 0 no matter what B you put in, because this thing was. Suppose I have a particular B field, which is a 0 mode of P dagger. Then when I plug that B field into this, what does it mean? It means no matter what C you put in here, you will never reach that small b. I mean, you will always get 0 inner product with that small b. So these 0 modes of P dagger are the spaces of changes of the metric.
But you cannot reach by this kind of.
That cannot be reached by an infinitesimal diffeomorphism. That are orthogonal to changes of the metric that can be obtained by infinitesimal diffeomorphism. Because that's diffeomorphism, Weyl transform, diffeomorphism plus Weyl transform, sorry, by gauge transformations. We're dealing only with the traceless part. We've removed the trace part. These B's are metrics minus trace part. So we've taken the Weyl transformation and removed the trace part. We can always get trace parts by Weyl transformations. There's nothing interesting in that trace part. But exactly as engineer said. There were these equivalence classes that you could get to by gauge transformation, by diffeomorphism and Weyl transformations. And the orthogonal directions to those in the space of metrics are the 0 modes of P dagger. Because any change in the metric that can be obtained by moving along one of these equivalence classes is orthogonal to these. So these are the motions not orthogonal to those created by gauge transformations, and therefore in the direction of changing the equivalence classes. Changing taus, exactly. So now we have an interpretation. The number of 0 modes of C in this ghost action is equal to the number of unfixed diffeomorphisms, which was F. What? Yes, because by definition, an unfixed diffeomorphism is a vector field plus Weyl transformation, which doesn't change the metric. But this is the operator that acts on vector field. How the metric changes under a diffeomorphism after subtracting out the Weyl transformation. It is the same thing. Okay, so the number of 0 modes of C is F, and the number of 0 modes of B is equal to M. The number of moduli you have to integrate, number of orthogonal directions, number of taus. And now we understand why we had to put MB insertions into the path integral and FC insertions, or 2FC. Yeah. You can a bit loose between F and 2F, holomorphic, anti-holomorphic. But we understand why we had to do that. Why? Because, you see, if you have a path integral over fermionic degrees of freedom, anti-commuting degrees of freedom, and you've got a 0 mode, that path integral is 0. Right? I'm giving you the identity that integral d theta of something independent of theta is 0. So, suppose I took this path integral here.
In some cases, when you find 0 modes of your Laplacian, you want to say this kind of thing, determinant, then you just omit 0 modes.
Well,
suppose you have a Laplacian,
Uh-huh.
the determinant you want to calculate,
Uh-huh.
you find the 0 mode.
Uh-huh.
Omit product over 0 mode.
I mean, you can do that as a mathematical operation, but physics either instructs you to or not. You know, you can define a modified determinant or something like that. But you have to take into account also the zero modes. Zero modes are totally crucial for a lot of physics. Okay, here this came with the zero modes. You're free to write it in terms of something omitted, but they have to take into account the effect of the zero modes. Is this clear? So because the integral over the zero modes would have given you 0, the fact that you have exactly as many insertions of the operators will make sure that it's non-zero, because from each of these insertions you pick out one zero mode and you'll get something non-zero in the end. So it's totally crucial that in the end we got a formula with as many insertions in B as there were B zero modes and as many insertions in C as there were C zero modes.
So does that mean that the non-trivial scatterings in string theory are completely fixed? For example, you mentioned the two-point function that's divergent. So for some manifold of a given genus, in very vague or imprecise language, the total number of asymptotic in and out states, are they completely fixed by the
No.
which yields some sensible number?
No, as you see, for instance, the total number of scatterings here was undetermined. F of them were fixed, had C insertions. The remaining of them were just integrated over the manifold. So there's no bound on number of insertions you put.
Yeah. I mean, you just gauge fix the numbers
that you need.
Yeah.
And the rest you continue to integrate. Notice that those that you gauge fix no longer are integrated over, but they have an insertion of C associated with them. Those that you haven't gauge fixed, of course, are integrated over. That's what it means not to gauge fix. And they have no C associated with them. Is this clear? Okay, let's say this a little more in little more detail.
So the P daggers will be some BRST operators?
No, BRST operator will be different. They'll involve the PP daggers, but it will be different. Okay, we'll study the BRST operator. That's the purpose of this course. This course we're going to go into every gory detail you never wanted to hear about. Okay, because the point of this course, many of my colleagues ask me, why do you teach world sheet string theory? Who uses it? It's true that nowadays string theorists hardly use world sheet string theory, with honorable exceptions. Okay, but the thing is that this is a whole body of knowledge that precisely for this reason you will not pick up while doing research. Like you'll learn how the rules of ADS-CFT, you'll learn all that kind of stuff. You will not just pick this up yourself unless you've taken a course or you really devoted time to studying it yourself. Now you have to make a judgment. You have to make a judgment about how important it is. How likely is it that in 20 years knowledge of this stuff will be key to the next great discovery? My judgment is that it's very likely, because it's very beautiful stuff. It's the heart of the subject. So that's why I'm teaching it, because I don't want you guys to leave TIFR without knowing this stuff, because it would be very easy to do it. And do well in your research for the first 10 years, and suddenly 10 years later there'll be a new development and you find you can't understand it all because you just don't have the background in world sheet string. And that's, maybe Harvard can do that, not TIFR. Okay. Okay, great. So, yeah, so for that reason we're going to, I'm not at the level of a mathematician, but for every logical step we will go through this course. We will understand everything. Okay, great. Now, I'm going to spend a little more time on this P operator. So, let's look at the operator. Indranil didn't like dealing with P because it was a rectangular operator. Okay, it took vectors to traceless two tensors. P dagger did the reverse. Now there is this operator, however, and suppose we look at P dagger P. This is an operator that acts on vectors and gives you vectors. Okay, so this is a nice square operator. This is an operator that can be diagonalized. Okay, so let us imagine we were on some manifold, take this operator p dagger p and we diagonalize it. Okay. So this operator has some eigenvectors Cm's and eigenvalues lambda. Any field C, any vector field C, because of completeness, it's nice Hermitian operator where a space with a well-defined inner product. Any field C, any square integrable field C, the kind of fields that we are interested in looking at, C alpha can be expanded as let's call it, so this is Cm sigma, Cm alpha sigma gamma m for some parameters gamma, for some coefficients gamma, because this is a basis, an orthonormal basis. What?
You should put the alpha and that's
On the V?
I mean on the coefficient.
No, this is a vector field. That's why it has an alpha index.
You're trying to express some general vector field in terms of the eigenvectors.
In terms of the eigenvector fields. The eigenvector fields are particular vector fields such that p dagger p on Cm alpha sigma equal to lambda m Cm. Okay? Now, how do we define the path integral over C's? One way of defining over all field C, one way of defining it is product over M d gamma m. It's a standard thing to do. Take a field, break it up in orthogonal basis, and the path integral is the integral over coefficients. Okay? Now, those lambda m's, sorry, those gamma m's corresponding to lambda m equals 0 are the coefficients of the zero modes. And the problem with your path integral is that the integral here has integration over the gamma zeros, the gammas that multiply the zero eigenvalue. But those don't enter the action. Those gammas don't enter the action because they're zero modes, the coefficient of zero modes. So that's why we needed, that's what I wanted to say here. We needed exactly f insertions of C, because in those insertions there will be these gamma zeros and you'll pick those out. Is this clear? Similarly for the B's. Now, is this clear everyone? See, what does the path integral over C's mean? It means path integrals over the ordinary integrals over these gammas from over all of the gammas. Now, most of the gammas enter in the action in e to the power s ghost. What is s ghost, by the way? No, CMs are just vector fields, functions.
CMs are
Bosonic. Gammas are fermionic. Yeah, because CMs are just fields. P dagger P is a bosonic operator. It's, you'll get a function, right? You get sin x. Yeah. Yeah. The gamma m's are numbers. This is a vector field of, it's a Hilbert space. So there are two vector fields. There are vector fields in space, and we're looking at the space of vector fields as a Hilbert space. CMs are the basis of vector fields in this Hilbert space. Okay? So their coefficients are numbers. It's like Laguerre polynomials. The CMs could be some Laguerre polynomials, Hermite polynomials, that kind of thing. So like, you understand. Okay?
Why do you say that let's see a graphic data because acting on 5
Yes.
you already take coordinate equation.
Okay?
Maybe like it.
Uh-huh.
So Hamiltonian epsilon psi is equal for P times psi.
Uh-huh.
The eigenfunction.
Uh-huh.
You had the bottom operator,
Uh-huh.
but the eigenfunctions that we have are Fermionic.
No, no. So let's take the Dirac equation, let's say. Okay, so what are the these kind of things for the Dirac equation? They will be like some e to the power I px, okay, times some columns, right? Where the columns have relative ratios which are numbers. So that part I'm calling the Cm, and then you can multiply by an overall number if you want, and that you can call fermionic. See, what you're doing is diagonalizing an operator on function space. See, you've got an operator. This operator, some differential operator.
So I agree that if you take gamma to Fermionic, there is no problem.
Huh.
I'm just trying to, it is necessary.
Well, I mean, it depends on your definitions. What I want is a basis in the space of vector fields. Vector fields are bosonic objects. And then I look at them with fermionic coefficients. They'll be functions of sigma. Maybe there's a matter of semantics here, but this is how I want to think about it. Okay. Okay. Now, I want to say a little bit more. Let us see. Look at this object P dagger P. Okay. Let me look at the quantity P dagger P on Cm alpha. Let's look at this equation. I'm going to suppress the alpha and the sigma index. Is equal to lambda m Cm. PCM. Now, I put my bracket here. You see that PCM is an eigenfunction of PP dagger with the same eigenvalue.
So PCM is B.
Is an eigenvalue of the B operator, of PP dagger, the operator that will be relevant to understanding the B path integral. This manipulation is correct except unless something happens. Unless what happens? PCM is 0. Because if PCM is 0, this equation is true, but it's not an eigenvalue equation. It's just telling you that 0 is 0. You see, I've identified, given an eigenvector Cm, I've identified a map. Cm goes to PCM. This map is always good, but this map takes me from non-trivial eigenvector to non-trivial eigenvector, only if PCM doesn't vanish. Exactly. And similarly the other way around. You see, we could do it the other way around. Exactly. So the spectrum of P dagger P and PP dagger is identical except in the zero mode set. Right. Okay? So, given a Cm, you can define a corresponding Bn. Okay? So we can separate out the expansion into the zero mode part and the non-zero mode part. Okay? In the non-zero mode part, for every Cm, there is a corresponding Bn, which is PCM. Okay? And in the non-zero mode part, what is the ghost action? Well, the ghost action was BPC. Okay? So now suppose our expansion is C is equal to gamma MCM and B is equal to beta MCM. Ignore the zero modes for now. Deal with them later. In the non-zero mode part, we plug this in. Beta, thank you, PCM. Thank you. So we get beta m gamma n sum over mn PC m p c n, right? But now we pull the p dagger there, so that's equal to sum over m n beta m gamma n cm p dagger p cn. But this is lambda n, so that's equal to sum over m n beta. Yeah, now we're going to get lambda. Of course they are orthonormal because they're eigenvectors of a Hermitian operator. So exactly. So thank you.
Unless they degenerate. I mean, then also we can.
You always choose.
Normalize it.
Yeah. Beta n, gamma n, lambda n. Sum over n. So you see, in this basis, the ghost action is simply e to the power minus sum over n beta n gamma n lambda n. Quite nice. Okay. Notice though that the sum runs only over the non-zero modes. What is the dependence of the ghost action on zero modes? It's 0. The action, the just because it's 0 modes, it just vanishes. Okay? All of the contribution of the 0 modes in this comes from these insertions. So you see, this formula is now very simple. If you want to, you can just do the integral over non-zero modes once and for all. Because the integral over the non-zero modes does not depend on the insertions. Why not? Well, C's here include zero modes and non-zero modes.
But then from those things you pick up the zero mode contribution.
Exactly. You have to pick up every zero mode in each of these insertions of C's. Exactly. You have to pick up all the zero modes. And therefore, the non-zero modes, that part is just not there. Similarly for the B's. So the integral over the non-zero modes of B and C, if you want, can just be replaced by a determinant of P dagger P. This is determinant prime, Infinitesimal kind of determinant. The determinant omitting the zero modes. Exactly. Exactly. Otherwise there is no information, but there might be important tau dependence. There might be, yeah. But the point is, you can, in principle, and this is not how we find it convenient to do, but in principle you could do it once and for all. Okay, this is, I will emphasize this when we are doing actual calculations. It will be easier many times just to use conformal field theory techniques to evaluate. It's not these determinants and so on, but just to know in principle. What about the zero modes? Now we can do the integrals over the zero modes. What do we have? So let's look at the C's. Okay, let's look at the B's maybe first. So we've got product m, so I is equal to 1 to m square root g del g alpha by del tau I b alpha beta. And then we have to do the integral. Now we argued that we can replace this entirely by the zero mode sector. So the total number of zero modes,
What is the contribution that comes from non-zero modes instead of beta?
nothing, zero. Because you see, everything is zero mode plus non-zero mode. And you get zero unless you pick up all the zero modes. Because there are as many zero modes as insertions. So suppose you picked up one less zero mode. Then you'd have more zero mode integration variables than insertions, and so you'd get zero. There'd be one zero mode whose integral d theta will have nothing to act on, and so
I mean, that will be infinity, right? I mean, if
Zero.
there are more integration variables.
zero because it's fermionic.
Oh, okay, right.
Yes. Okay, so you only have to keep the 0 modes. So in these B's here, okay, in these B's, what you're supposed to do is to replace this B by just the sum over 0 modes. So let the sum over 0 modes be, I don't know, B's 0I, beta 0I. Okay? Now we have to do the integral only over the 0 modes for this part. So integral d beta 0I.
The determinant of beta.
What?
Determinant of beta is
Determinant of
the answer for this B integration.
Exactly. The answer for this B integration is going to be the is going to be this quantity. This B has an alpha beta. I'm getting a little confused about position adjustment. Where did that come? Where did that come from? So let me remember. So the sigma dependence is confusing me. Just to admit. What is happening here? Yeah, just give me 1 second. Just look up one thing. Yeah, it has the formula with an integral. Where did I miss the integral? This is supposed to be integrated over. Yeah, where did I miss that? Sorry. Somewhere I blocked. What? Yeah. What? No, the integral over sigma. These are functions of sigma. and this was supposed to be integrated over sigma. Now, where did I, just why didn't I have that in my formula? Just a minute. Yeah, it should have been there, right? Because the change in the metric, right, should have been there, right? Just a minute. Where did that come from? Sorry. I'm saying that I missed somewhere a signal.
The term was sitting in the action, right? And then we brought it down. So action has integration of what it is.
Yeah, you're probably right. Let me just remind myself where it came from. So what we did was introduce an integral d tau, integral d omega, delta of g omega, g naught omega minus g, and some delta functions for the c's. Let's forget about that for a moment, the positions, times delta Faddeev-Popov. And then what we did,
When you wrote it as an integrator, e to the power something. Then you wrote e to the power integration of something.
yeah, right.
Because at every point in space-time you want to impose this condition.
Right, exactly.
Therefore there is an integration of space-time.
There was an integral. Exactly. Sorry for that. Exactly right.
But still you have more and more index in this equation.
What do you mean?
Del g, del tau I.
Oh, sorry. Yeah, del g, del tau I, and for every one of these, there was an insertion of beta. Yeah. So there was beta. So here, there was one such insertion for each one of these. That's good.
Every tau I direction had a factor of del g, del tau I.
Del g, del tau I, and each of the.
One factor of b.
Okay, so let's forget about this for a moment. This is a factor of b of alpha beta. Yes, b alpha beta, exactly, integrated. So far so good. Now we're going to take this, so now let's write this in slightly more convenient notation. Let's write it in this inner product notation. Okay, so this is integral del g by del tau I times b. And there's a product I is equal to 1 to m of these. Okay. Now each of these b's, in each of these factors I'll expand these b's in the zero modes.
That is another index.
Yes, exactly. So I will expand this. So let's say that on the ith guy, I will expand it as so del g by del tau I, and I will expand as the zero mode index. Let's call that beta I0. These are just this times times beta I0 times b I0. Or what I call them, sorry. What were the functions? What had we used for the zero mode functions? Let's call that b I0s. These are the eigenfunctions. And beta I0s are the numbers. Yeah, that's a good point. So J and J.
Now it will look like a matrix.
Yeah, that's right. And we want to do integral product d beta J0.
Every term in
once you integrate, it's a sign times this inner product kind of thing.
Right. So now what we get is a product of these guys, of these various terms, but in every kind of order with a sign. So it's basically a determinant or a Paphian or something like that. It's basically a determinant, product of matrix elements with signs.
Minus sign, therefore really
A determinant. So this is going to be determinant, it's proportional to it, determinant of del G by del tau I beta j, B0 j. See, so what is this? What we want here, so what we want is a product of such terms, okay? And we have to do this integral. Now what does this integral pick up? This integral picks up all terms with exactly one factor of every d beta j0. These are fermionic. Okay? So you'll get one factor of each of these terms, but with signs. That's basically a determinant. Okay? So this part here, the part over the integral over moduli, gives us this determinant. And this determinant, the whole effect of all of this is to tell us when we integrate over moduli, with what measure should we do the integral? You see, there was this space of inequivalent metrics that were not related to each other. What? No, it may not be independent. But this is an intrinsic measure, and there may be other things that also care about that measure. But I have to integrate this with some measure.
So we parameterize tau by the 0 or that as a measure?
Yeah, exactly. So see, so suppose we've got, suppose we've got a parametrization of taus. I change my parametrization of taus. Okay, that changes the integration measure. Right? If I do integral d tau I, you do integral d tau I prime, where tau I prime is some function of tau I. That's not the same measure. Okay?
You are telling me that this linear transformation that cancels this determinant.
Exactly. But just because the determinant comes with a 1 by tau, and determinants transform like by product of the, let's do it. Okay. So this quantity here, okay, del G by del tau I under a change of variables is equal to del G by del tau j prime, del tau j by del tau I. So this matrix is a matrix product. Determinant of product of matrices is product of determinants. So you get an extra factor of the Jacobian, which exactly cancels the change in measure. Okay? So this, had it not been for this determinant, the formal procedure, integrate over moduli, would have been an undefined statement.
You should have cared about
how you parameterized. Exactly. This beautiful determinant here is precisely doing the job of giving you a coordinate invariant formula.
This is the square root G.
That kind of thing. Okay? So this is another way of seeing that you have to have some such factor. Unless you had some such factor, the quantity was neither right nor wrong, it was just ill-defined. Different ways of parameterizing moduli space would have given you different answers. But because of this factor, this is well defined.
But in this thing that you have, every other tau dependent
Yes.
should come in such a manner that if you raise indices with this, they are singular. Only then you get something which is independent of two class of coordinates. I am saying that this is the part which is the measure is sort of a degree of material invariance in the space of moduli. This
invariant.
Scalar, yes.
Yeah, all that you are saying is that it should depend on the modulus. Should be some function of the modulus. Clearly there are no indices anywhere else in moduli space. It's some function of the modulus. Any function of modulus. Because now you the only principle is that you change.
If you take the given the tau is a vector. You do tau equals to constant matrix times tau.
Wait, tau is not a vector. Tau is a set of parameters.
Yeah, I made them into a vector.
Oh, okay.
Tau 1, tau 2, tau 3, make it a vector.
Correct.
Tau vector goes to some constant matrix A times tau.
Right.
This is the coordinate set.
Yes.
And in this you will get a Jacobian.
Which is cancelled by this.
This will get cancelled by this determinant.
Yes.
And if you had some explicit tau dependence,
Yes.
that will have the factor of A.
But because it's a change of variables, it's like general relativity. You get square root g times any scalar function.
It is a scalar function. Anything that is scalar under this coordinate set.
But you know the function could be x square.
X square is allowed. So all the tau dependencies are allowed or some specific tau dependencies?
Any tau dependence is allowed.
I mean, and the total function has to be.
It should just not change under. We're just doing a change of variables. Let me.
In other words, always there should be a sum over I. All the relative factors should be 1. So can we have a term like this? Tau 1 square plus 2 times tau square plus 3 times tau 4 square.
If the taus are inequivalent coordinates, you can have anything. You know, you've got a space. See, you've got a space of taus. You have to sum over that with some weighting factor. So you have to assign a volume and then an arbitrary weighting factor depending on where you are. There's nothing else.
This quantity multiplies, let's say, sum over tau I.
Sum over tau I. Yes. Tau I is a, there's no vector space in. Good. Anyway, please go on.
Suppose the final integration is d tau I
Yeah.
times this determinant.
Yes.
Nice measure this is.
Yes.
And then let's say tau 1 square.
Yes.
Only tau 1 appears.
Yes.
Then once you try to do the integration,
Yes.
you will get some answer. And if you make the variables into tau tilde,
Yes. You get the same answer. Right? I mean, it's just change of variables. Maybe a. Not at all. I'm saying something very trivial. I just want. Let's do polar coordinates to Cartesian coordinates. It's that kind of thing. Okay, so two dimensions. So I have x1, x2. Okay, integral square root g, any function of x1 and x2 is equal to integral square root g dr d theta, the transformed function of r and theta. That's what I'm saying. Yeah.
by definition, this function will be transformed in another case.
That will make it work. Yeah.
So if I had tau 1 initially, it will not become
Tau 1, it'll be whatever it is in the new coordinate.
It will not be tau 1 tilde, it will be tau 1 tilde times whatever.
Whatever was tau 1.
Yeah, by definition, this is
Yeah. No, that's, yeah. Good. Okay. Oh my. 2 minutes. I'll just finish up this this last part. Okay. So far we've dealt with the moduli. Let's deal with the ghost insertions. Okay. So now the ghost insertions, how do they go? We had a product of we had a product of D.
So this was the ghost insertion, right? Given this model, I mean, the B ghost.
The B ghost. Let's deal with the C ghost.
C ghost, yeah.
Okay. We had a product of, yeah, this is just sort of simpler. Because what we had is a product of C, well, let's do it. We had a product of C at sigma I zeros. Okay? And those we had to expand in the zero mode sector. So we'll do as we did before, Cj0 of Ci zeros. Okay? This is which function, this is at which point. And the same kind of logic will give you a determinant. Okay? So you will get determinant of Cj of sigma I0. Which field and which point? Okay? There's not a check here because it wasn't a measure. We weren't doing an integral over unfixed diffeomorphisms like we were doing an integral over moduli. Okay, so it's not like it transforms in a way a measure should, but just this is the quantity. So in the zero mode sector you got these determinants, these two determinants. In the non-zero mode sector you've got this quantity, and then you've got whatever you got from your from the integral over x's. This is what you have in your hands. Okay. Now there is just one thing I wanted to say, but we're running out of time. And
So there is no relation between M and F.
there is no relationship between M and F, though we're going to find well, you know, at this stage we've not discovered a relationship between M and F. We're going to see that M, the number M and the number F are related to the genus.
So I should probably clarify this one.
Go on.
So the M's are the directions which you cannot reach by just doing either while or diffeomorphism, right? M is this radius of this orbit you were drawing. Right?
Yes.
And F's are
Those while plus diffeomorphisms that leave you fixed, that don't move you.
okay.
Then we'll be on the same circle.
Same, not on the same circle, at the same point.
Same point.
Yeah. Okay, I wanted to explain to you that. Okay, now the whole thing we haven't yet seen it all makes sense. There are many things we have to check. One really crucial thing is we have to check that the whole formalism is while independent. And it didn't look like it, right? In our discussion of conformal field theory, we had non-trivial while dependence. The only way it can work is if the while dependence from the B and C ghosts cancels the while dependence from the X fields. Quite remarkably, that happens when D is 26. Okay? I don't have the time to show that to you today, and I'm really sorry, but tomorrow I'm traveling, so tomorrow's class we can't hold. It's really, we'll have to find some extra time for these classes. But let me, it'll be next week when I show you this while dependence cancel. But as preparation for that, I would like to understand one thing, and that is this. Let us work in a space where the metric, at least locally, and actually I'll show you, you can always patch by patch locally do this, that the metric locally square is e to the power 2 phi dz dz. Oh, or maybe even, anyway, yeah. maybe we should leave this for next time. It's going to take time. It's 7:35, 7:30. Okay, in the next class we will analyze the ghost action more carefully here, and I will explain to you what I wanted to explain to you, but I'll do that in the next class, is that C is equal to a -1 field under conformal transformations, but B is equal to a 2, 2 field. Or more precisely, the analytic part of C is a -1, 0 field. You see, let me quickly say something. Let me see it properly. The C field has a Z component and a Z bar component. So there's a Z analytic part and an anti-analytic part. The B field has a ZZ component and a Z bar because it's traceless. So just like the stress tensor. Okay? So now in this coordinate system there's a natural split of B and C into analytic and anti-analytic. And we can ask what the transformation properties are of the analytic parts of C and the anti-analytic parts of C under conformal transformations. Okay? And the answer comes actually very, in a basically trivial way. Let me tell you how it comes. How did C transform under diffeomorphisms? Well, what was C? It was a vector field. So it transforms under diffeomorphisms like a vector. How does it transform under wild transform? Well, it doesn't transform. It's a vector. What about B? B was like the metric. Okay? So by using that logic, the trace part of the metric transforms under wild transformations. But B is the traceless part of the metric. So the traceless part of the metric also doesn't transform under wild transformations, but it transforms only under diffeomorphisms. So C transforms exactly like a vector field transforms under diffeomorphism, and that transforms like the analytic part of that transforms like a 1, 0 tensor. The anti-analytic part transforms like a 0, 1 tensor. B transforms exactly like a traceless 2 tensor with 2 indices down, transforms under diffeomorphisms, and therefore transforms like the analytic part transforms like 2, 0, anti-analytic part like -2, 0. Now you might wonder, what if I lower C? 0, 0. Okay, the anti-analytic part. You could ask, okay, this is okay, but what if I dealt with the lowering of C? Yeah, that should transform like a +1, 0 tensor. How does that work? And the reason for that is that the lowering of C involves a factor of the metric. Okay, so the natural objects to deal with, the objects in terms of which, and this is the clean statement. What I wanted to show you, we will do next time, is that if you work with lower C objects, raised C objects and lowered B objects, the action does not involve any factors of the metric. Okay, this is the thing I wanted to show you. Okay, in fact it's almost obvious, but anyway we'll do it next time. We'll do it next time. Okay, and so these objects, the ghost action is while invariant. It's conformally invariant, while invariant. If C transforms like a upper tensor, a vector field, and therefore this assignment, and B transforms like a 2-indexed upfield. I'll show that to you next time. 2 minutes of algebra. Once we have this, we will then figure out. Now we will then deal with the BC system as a conformal field theory. We will figure out its stress tensor, and we will figure out its central charge, and we will see that C is equal to -26. And this will tell us that this whole system is while invariant, but only in 26 dimensions. Okay. So the constraint that we got from Lorentz invariance in our first crude attempt will come out from another related constraint and consideration from this way of it. But I'll have to show you that next.